So this is the second of the two talks. This one is more software and hardware oriented than diagnostics. So if you have any software experience, you will probably find this quite interesting. My background is software, so I find this interesting. So if you came to the first talk, you'll see here's the same caveats. I am not a formal engineer. A lot of my experience is Williams-based. You can think in terms of things that you're familiar with. In this case, it will be street addresses and neighborhood blocks. Things we will be covering, fundamentals, schematics and boards, software, the processor, and the microcomputer, the board itself. Please hold all questions until the end. Okay, so some of this I covered a little bit earlier, but it's a little bit of a different slant. The electrical side, you need to have some fundamentals. Voltage is AC or DC. In the world of software, it's DC only. There is no AC in the world of software. Semiconductors, very important for this. They are essentially DC devices, valves. They only transmit current in one direction when a forward voltage is applied to them. A transistor is basically made up a whole bunch of diodes. You need to know about binary, base 2. In the software world, people refer to this as false or true. I generally refer to it as false or not false, because it's 0 or not 0, because every other number that is not 0 is considered not false. Some people like to refer to it as 0 or 1 or false or true. Like I said, I don't like doing that because it's not strictly correct. In the world of hardware, people will generally refer to signals as high or low. A low signal is defined as 0 volts, and a high signal is defined as a logical 1, but it could be 5 volt or 3.3 volt or whatever your high voltage is on the system that you're using. You need to know a little bit about logic families, and they are not compatible with each other under certain circumstances. The most common thing you'll see in a pinball machine is TTL, transistor to transistor logic. It operates at 5 volts. The definition of a low signal is anywhere between 0.8 volts and 2.0 volts. Definition of a high signal is anywhere, well, that doesn't seem right, from 2 to 5. I think I may have transcribed that incorrectly, and I'll have to double check that later because that should not overlap. There is an area in the middle that is the gray area. So, yes. CMOS, for 5 volts, the definition is there, 0 to 1.5, and high is 3.5 to 5. And CMOS for 3.3, the definition is there. Again, pinball machines use TTL, and it's 5 volts. So, hardware, fundamental logic gates. Logic at the hardware level, not the software level. Again, if you're familiar with software, you'll probably be familiar with all these operations, but they're quite different in the hardware world. A buffer in a hardware world is just a straight signal in equals signal out. A NOT gate in the hardware world is basically a signal equals a NOT, which in the hardware world is referred to as an inverter. They don't call it NOT. Software calls it NOT. And 2 inputs, 1 output, A and B. You'll be familiar with that if you've seen C syntax and notation. Or same thing, A or B. And those are bitwise rather than logical. But it's effectively the same thing for all intents and purposes. NAND, this is something special for the hardware world. You'll see NAND gates. You won't see that operation in the software world. It's just an AND operation, and you put parentheses around it and then invert it or not it. NOR, it's the same thing. XOR is a special operation where the signals have to be either 0 or 1 in order to produce a 1 result. And XNOR. In a lot of the hardware world that I've been involved with, I've almost never used the XOR or the XNOR gate. I've only used AND, OR, and a NAND and NOT. Truth tables. This is a hardware concept. This is not a software concept. Truth tables document all the input and output cases. For 2 input devices, that's a 2x2 matrix, 4 results. If you are all uncertain about anything, consult the data sheet for the integrated circuit. The data sheet contains all the information that you will need. It is often buried amongst a ton of other irrelevant information for your purposes, but it is there. A typical AND data sheet, both inputs have to be 1 to produce a 1 result. And that is exactly what's described there. If any of the inputs is 0, you get a 0. OR is the exact opposite. Both inputs have to be 0 to produce a 0 result. If either input is 1, you get a 1 result. It's exactly how you think of it in English. AND is both, OR is either. Schematics. Logical. Okay, so a schematic describes logical function or connection. Do not think of a schematic as anything that's physical. It is just how the circuit should work at a logical level. A good example for thinking about the difference of this is redundancy. If you've ever worked on a RAID, there are RAID 0, RAID 1, RAID 0 plus 1, RAID 5, RAID whatever you want. But the computer sees only one logical storage device. The backing of the other end, the physical hard drives that back the store, can be configured in a whole different bunches of ways. The computer only sees one logical device. It's the same thing here. The schematic is the logical description of what it is. How it's implemented doesn't matter. So yes, and that follows on to read the schematic to understand how the design is supposed to work, not what it actually looks like. On a schematic, symbols represent functional units, lines represent connections. Physically, they will be wires or copper tracks. Connections may be labeled to make it easier for you to understand what the connections actually are and what they mean. The connections may be grouped, the mythical bus, which we will cover later. And sometimes you will often see symbols labeled with a prefix, a tilde or a slash. And this indicates that the signal is active low. So what do I mean by that? Well, normally you think of a signal as on or off, and on is 1 and off is 0. But sometimes in the signal world, if activating it means the signal is off, that name is often prefixed with a tilde or a slash. I like to use tilde. I know some people like to use slash. It doesn't matter. It's just a way to say this signal is active low. You will also see a horizontal bar placed over the symbol name. That is also another way that the symbol is indicated to be active low. The most common thing you'll see is the reset signal is active low, and often the name reset with the horizontal bar over it is what you'll see. That means that when the line is low, reset is active. When the line is high, reset is not. The processor comes out of a reset. So this is what a sample schematic will look like. This is all a bunch of logical connections. So pin 1 of J2 connects to pin 2 of U1, and so on and so forth. And I've named the symbols there, the lines, so that you can see what's connected to what. And I've done it logically. U1 has 1A1, 1A2, 1Y1, etc. Same with U2 and same with U3. And then for completeness and correctness, I put the power symbols all the way on the left there as the input. It's irrelevant. The reason why I want to show you this example schematic is they're identical. There are 3 identical circuits there connected to U1, U2, and U3. They all look the same. They're all functionally the same. But as you'll see coming up, they're going to be very, very different physically, even though they look the same logically. Schematics and boards, physical. The board is a physical layout, a represent of what is in the schematic. The connections on the schematic are the wires, but on a physical board, they are copper traces, often covered with a solder mask. But if you remove the solder mask, you'll see there's copper underneath it. The physical route of the track is not described in the schematic. Again, logical versus physical. Tracks are located on a layer of a board. The copper has to occupy a physical space on the board. And you know what? Because it's physical, they can't cross each other. It's like a maze. And the way to work around that is that you can put copper on any layer that you want. You can have multiple layers. Don't have to have just one layer, because if you had one layer, you wouldn't be able to lay the board out. In the late 80s and 90s, actually earlier than that, they would manufacture boards with one layer or two layers, very typically. Single layer or double layer boards. Single layer boards are cheap, one layer of copper, you're done. All the copper has to be on one layer, which kind of restricts what you can and can't do. Double layer boards, you can put copper on the back side of the board. Nowadays, they're manufactured with multiple layers that are embedded inside the fiberglass substrate. You can't see the layers. That's why you need the schematic when you want to fix one of those boards. The tracks between layers are connected by what's called a via. It's a small little hole that is drilled through, typically on a double layer board, from the top to the front of the board and connected with plating that creates an electrical continuity between the top and the bottom. In multi-layer boards, those are buried vias. You can't see them. So multi-layer boards, I don't deal with them. Too much for me. Most boards in the manufactured in the 80s and 90s are single or double. There is a big difference between a single and a double layer board. A single layer board has no plated through hole. So often, like for example, the Williams lamp boards will be single layer, and you'll find that the pins that are soldered often will have cracks at the solder joints. And the reason why is that there's no plated through hole for that solder to wick into, and it just builds a big pile right next to the pin. When you start doing enough soldering, you'll be able to tell the difference. When you apply solder to a plated through hole, it wicks into the hole and transmits through to the other side. It's a very, very different look and effect. So this is a diagrammatic representation of that previous schematic with the three identical circuits. And the lines cross all the different places for that 5-volt ground correctness. But really you can see that there is a dip at the top left, a dual inline pin, and at U1. U2 is what's called an SOIC, small outline surface, a surface mount IC. And U3 is a thin shrink, small outline plastic, even smaller IC, outline. But you can see the logical connections in the schematic were all identical. The physical representation is very, very different. The chips are different. The connections and the copper traces to them are different. And this is what I'm trying to make the point. Is like the schematic is logical, the board is physical. If you can't look at this and it kind of doesn't make sense to you, well, that's what the board would look like. 3 identical circuits, 3 completely different layouts. And this is just a very simple, contrived example. It can get much, much more complicated than this. Always use the schematic to look at the logical connections. Follow the copper traces, if need be, to find where they are physically connected. So a small sidetrack to inspection, how to look at the signals. Tracks conduct signals, it's electrical, between points in the schematic. The tracks will often be exposed at pins where you can probe. So if you have a logic probe, you want to get your logic probe and point it onto the exposed pads, because you need to be able to actually see what the signal is. Typically, I like to use a logic probe because it's really very simple. I just want to see whether the signal's high, low, or pulsing. I don't care what the waveform is, I just want to know that it's changing, because if the signal's changing, the circuit's probably working. No need to see if it's square, I don't need to know what frequency it's running at. But if you're in the analog world, often you'll need to see what the voltage is and the frequency and all that. And to do that, you need an oscilloscope. As it says here, logic probe detects high-low pulsing, has restricted resolution. The logic probe will produce audible feedback with tones, and to give you an idea of what the signal is. Again, it's not good enough to detect how fast things are going. A good example is you really can't use a logic probe on a 4 megahertz frequency clock. It's just not fast enough. To see that 4 megahertz, you're going to need an oscilloscope. And as I said there, for analog, analog is voltage related, which is why you need the scope. Logic probe deals in 0 or 1. It's logic. Okay, so now we're going to sidetrack a little bit into the software world. If you know anything about it or you've programmed for a while, you'll probably know what radix is, but we'll just get to the same baseline. Radix is the base that you're using. Everybody here hopefully has, 10 fingers and 10 toes, and that is radix 10. You are used to counting in base 10 because your currency is base 10, and if you live in a metric world, all your measurements are base 10. In the computing world, everything is base 2. It's binary. It's either 0 or it's 1. You can group those zeros and ones into bits, and 3 bits makes octal, and 4 bits makes hexadecimal. Octal is almost never used nowadays. I've never encountered it, and I'll tell you, I can't count octal. No chance. Hexadecimal is much, much more common and used, and if you program in the C world, you'll see the 0x prefix. If you program in the 8-bit microcontroller world of 6502 or 6809, you will see the dollar prefix. It's the same thing. It's just a hexadecimal number. And essentially, when you count, instead of counting from 0 through 9, and then 10 through 19, and 20 through 29, base 2 binary goes 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, etc., etc. You've probably seen enough of it if you're experienced with software. Another key point to remember is software is 0-based. It is not 1-based. If you're used to buildings and floors, you enter on the first floor. Not in software, you enter on the 0th floor. That's just how it works. Number representation, typically, and we'll keep it simple here for 8-bit numbers, but numbers can either be signed or unsigned, and a processor will treat a comparison different as whether you're using a signed or unsigned. I just mentioned there 2's complement, again, if you're familiar with these number representation schemes. The signed bit takes away one of the available bits. So if you have an unsigned number that's 8-bit wide, you have a number that is represented as 0 through 2 to the power of 8 minus 1, which is 0 to 255 or 00 to FF. Because the signed bit takes one bit away, it's 2 to the power of 7, and 0 is considered positive, yet it itself doesn't have a sign, which is why you see the number range there from minus 128 to 127. And if you are familiar with more modern systems with more than 1 byte, you'll have to deal with endian. I'm not going to get into that. So the software programming model for one of these old 8-bit microcontrollers that you'll see on these Bally's and Gottliebs and Williams is there is typically data registers. The data registers there's 2 of them typically, except the 6502 only has 1. They're called A and B registers. They're accumulators. They're there for general purpose arithmetic. They're like scratch pads. Processor does the arithmetic and stores the result in the register. The X and Y registers are index registers, and in the 6502 world, those are 8-bit, and in the 6809 world, those are 16-bit. And I think there's only 1 register in the 6809, the X register. They're used for addressing indexing. There are special operation registers, 16 bits wide, that the processor uses, the program counter, the PC, and the stack pointer, where stuff is placed onto the stack. There's typically one special purpose register for status and condition code, and these are things that store the processor's results of computation. There are primarily 4 main result flags. That one interrupt flag doesn't really count. The carry flag, when a carry operation has occurred, that's like when you add 9 plus 5 and you get 14. There's a carry there over the 0th portion. Overflow is specific for signed arithmetic. It's when a result has caused the sign bit to change, or an arithmetic operation has caused the sign bit to change. The overflow bit will be set. The 0 flag is if the result is 0, and this is why I referred to it earlier as false or not false, because the 0 flag is often an implicit comparison by a processor. Exception is PowerPC, you had to use the dot for that, otherwise the Processor would not waste any cycles trying to do it. The negative is the same. It's a comparison against 0. If the result is considered negative, the negative flag is set. Some processors have special modes called the decimal mode, where instead of adding hexadecimal numbers, it will add decimal numbers, and it will clock it over instead of using hexadecimal. That's beyond the scope. All processors have different operation units, instructions, typically grouped into load stores, arithmetic, add, subtract, or logical, and or. There's a compare unit that allows it to compare signed, unsigned, less than, greater than, equal. There's a branch unit that decides whether it needs to branch or not. And there are a whole bunch of other miscellaneous things like flag operations, transfers between registers, stack pointers, and blah, blah, blah. A processor works in very simple steps. There's fetch, decode, and execute. That's pretty much what it does. Fetch the next instruction, decode, execute. More modern processors will overlap those in different cycles, but these old 8-bit microcontrollers did everything in one shot. They didn't have an instruction cache. You could write self-changing code. You could violate all the rules that you can't violate today in modern processors. Signal. So now we're going to go more to the hardware side, because if you're familiar with software, you probably would have seen all those things. But the hardware side is a little bit different. The processor is the brains. It communicates with the rest of the board with pins, the pinout. And if you've looked at modern Intel processors, I think they're like BGA with a gazillion pins and blah, blah, blah. And I don't know anything about that. It's too much for me. I'm simple. I like to keep my stuff 8-bit and 16-bit. That way I can count it. Nonetheless, the processor has pins that communicate with the rest of the system. They're input or output or bidirectional. The input pins are usually signals that come in from other places, like a reset signal. Output pins are usually things like address bits that tell what the processor is trying to access in the system. And the bidirectional ones are usually the data bits, D0 to D7. And this is what you'll see in the data sheet. You'll see exactly which pin corresponds to which signal. And in this case, it looks like they're using the horizontal bar to indicate that the signal is active low. Some of these signals you don't need to know about. Some of them you do. The address bits and the data bits are very, very relevant. The RW bit indicates whether the processor is doing a read or write operation on the bus. The reset signal is whether the processor is to be held in reset. The VMA is an interesting one for this particular processor, valid memory address. So if the address bits are valid, then that signal is set to high because it has no horizontal bar over it, so it is active high. So these boards that you'll see in things like Williams, System 11, WPC are basically microcomputers. They have a processor and a whole bunch of ancillary chips that support operation. In a late 90s, early 2000s style machine, you could think of it as the CPU slot with a south bridge and a north bridge. Nowadays, everything's all integrated into one big chip that does everything. But in those days, they had separate chips to do separate things, and they were pretty simplistic. On these boards, System 11s, System 7s, and whatnots, you will find there is a processor. Typically in Williams, it's a 6802. In WPC, it's a 6809. You'll also find a bunch of buffer and transceiver chips. And I've written here to satisfy fan in and fan out. And I will not go into that because it's a hardware concept that is beyond the scope of this topic. You'll also find storage, both volatile and non-volatile. And this excludes NVRAM, which even though it's non-volatile, we won't talk about, because as far as the software is concerned, it's volatile. It's RAM. It's SRAM. Non-volatile is ROM, either mask ROM or EEPROM, electrically erasable. Either one, UV or electrically erasable. And then as part of a machine, you'll find that there are also peripherals. Switches, lamps, solenoids, all controlled through, in System 11, peripheral interface adapters. And in WPC, controlled on the power driver board itself with all the transistors there. And the WPC will be touched on very briefly, but I think a lot of this the focus of this you'll find is System 11 because it's easier to understand. A lot of the System 11 address decode was embedded into that big 84-pin WPC ASIC, and it's a black box, and you don't want to know about it because you can't see inside it. You can see inside it on a System 11 board, which is why I want to spend some time covering it, because it's easier. So this is the System 11 board, and this is the layout diagram, and I've color-coded each of the boxes there to give you an idea. The green is the processor, the yellow is the non-volatile storage, the orange is the volatile storage, the SRAM, the red is all the peripheral interface adapters for the peripheral. In modern terms, you can call that a south bridge. The blue are the transceivers and buffers, which buffer the address and data bits from the rest of the system required to satisfy fan in and fan out. And the magenta ones are a group of ancillary logic chips that do what is best referred to as address decode. And that is for the address bus, and we'll cover that coming up. Here we go. So, a bus is a collection of related signals. In this case, address or data is typically what you'll see. The address bus is 16 bits wide, the data bus is 8 bits wide. These are separate signals, D0 to D7, A0 to A15, but you can think of them logically as one group of signals. The address bus bits refer to address bits only. The data bus bits refer to data bits only. The reason why they use this way of thinking and the representation in a schematic is it's easy to draw one big line with crosshatches through it that represents all the 16 bits than it is to draw 16 individual lines running all over the diagram. It's just these bits logically work together. We'll just treat them as one logical functional entity. However, when you look at them from a board, they are separate signals. 16 signals in an address bus, one line on a schematic, 16 copper traces on that physical board. And here's what it looks like in a Williams schematic. You'll see that those big crosshatched blocks are the buses. And in fact, they've been so kind as to label it address bus and data bus. And in fact, in this diagram, they've even kindly crosshatched them in opposite directions, so you know which one's address and which one's data. And it's very consistent. The green is the address and the red is the data. And you can see where the signals come off of the bus that they've put this line and labeled each individual signal bit that's come off the bus. The data bits almost always come off together because they're grouped as 8 bits of data. The address bits often come off in different places depending on what signal the logic is interested in. And you can see right up there at the top right-hand corner, there's the A13, A0, and A1, and that's a peer. And what that peer is doing, the peripheral interface adapter, what it's doing is it's looking at those address bits to see whether the signal coming off the processor is destined for it. Each peer will respond to the address bits and say, is this signal for me? And if it isn't, it'll just say, oh, I'm not interested. But if the signal comes out and says, oh, this address is me, you're touching my address, then the chip becomes active and starts looking at data. And we'll come to that later as well. More on the address and data bus. The processor communicates with the system primarily through these two buses, obviously. The data bits are basically just data. It's whatever the software is trying to transmit through the system. Nobody actually inspects the data for the most part. It's not always true. There are bank switching or I guess bank switching is probably the best way of saying it, where you can select different banks based on rights to certain addresses beyond the scope of what I'm going to discuss. Sometimes you'll see the data bits being addressed, but usually it's the address bits. So the address bits communicating which processor. The peripherals, as I was describing earlier, contain an enable or select that you need to typically active low select it low, and then when you meet those conditions, the chip will say, oh, this signal is for me. And then it'll wake up and start looking around. Otherwise, the chip says, this is not my signal. I don't care what you put out there. I'm not listening. There is almost always supporting logic on the board, and that's the address decode, which we will cover. So this is what the storage chips look like. The left one is a RAM chip. The center one is a 256-bit EEPROM ROM chip. And the right one is a peripheral interface adapter, PR. And you will see on each of these chips, there is an E. That's the enable bit. There's actually an E2 on this one, and I'm not going to get into that. It's compatibility. There's an E on this chip, and on the peer, you'll see they refer to as the CS. CS0, CS1, and CS2. They're chip select signals. And you'll see again this notion where CS2 has the horizontal bar above it, and CS0 and CS1 have none. That basically means in order to activate this chip or select it, you need to send a high signal on CS0, a high signal on CS1, and a low signal on CS2. When those three conditions are satisfied, the chip wakes up and says, you talking to me? And it starts listening. On the ROM chip, it's just that one signal on pin 20, the E chip, the E signal. And on this RAM chip, there's actually two. There's a low on pin 20 and a high on pin 26. So you may ask yourself the question, well, why would I care to have, like on the peer, why do I have three signals? Why not have just one? Because I'm either active or I'm not active. The reason why for this is that it allows the board designers to send different signals if they do and don't want to activate on other signals. In essence, it's built-in address decode on that chip. You don't need to supply an AND or an OR chip that's sitting off on some other part of the board. The chip's got it built into it. You just need to supply the relevant signals. If you only need one signal, then you can tie those pins that you don't need to high or low to satisfy the chip select condition. That's the easy way around it. That's why oftentimes you'll find chips have multiple chip enables or chip select signals. Anything you don't want, just tie it to what it should be. It's either always high or always low. So, I guess most of you people here probably have software experience, but if you don't, I will try and explain what the address bits are and how to think about it. The way I like to think, I've done this for a while, so it's kind of second nature to me, but if you haven't, the way to think of address bits is like on a street. You have different blocks on a street. You can divide the street up into 10 blocks, and each of those different blocks can be selected by different bits. And you can further subdivide those blocks if you really want to into houses on that block. If you want to take it to a higher level, you can think of like cities across the country and then suburbs within the city. But it's the same thing. You're just taking areas addressed by each bit and grouping them together. That's pretty much all there really is to it, but I like to think of them as that way. How the granularity to which you go will dictate how many bits you need to look at. In the address world, often a select number of bits will be used to address the chip itself, and the other bits will be used to determine whether the chip is actually selected, the chip select sites. And often, particularly in this system, the System 11, it's address bits 15, 14, and 13 that determine which chips are addressed where and how. And it's the decode that does that. Again, street address enabled. I like to think of it that way if you're unfamiliar with it. But after a while, you see enough of these hex numbers, it becomes second nature. So this is the address map. Hexadecimal. It's just, there's 16 bits. I'm not going to write out binary 16 bits. This is how it works. System 11, there is a 6116, which is a 16 kilobit RAM, which turns out to be hex 800, 2048 bytes, if I remember correctly. The rest of that from the portion of 800 to 2000 is not mapped. You can touch that address all you want in software. There's nobody listening. That goes into the ether. 2000 to 4000 is where all the peripherals are located. And 4000 to end of address is code. In earlier systems, I think it's system 6, there was only 15 address bits. So all they needed was 4000 to 8000. And address bit 15, the highest bit, was just ignored. You could just double up and do what you want. In system 7, Williams needed more code space, and they used address bit 15. Here, they used the address bit 14, 4000, to actually expand the code space even more. And in WPC, which we'll cover below, they extended it even further. And WPC is a different layout, but it's very, very similar. The first 2000, 8K, is SRAM. It's a 6264 chip, which is 64 kilobits or 8 kilobytes. The 2000 to 3FC0 range is dot matrix pixel buffers. I'm guessing in the early days of WPC, that was just unused because they had alphanumeric displays like you see in Funhouse. That just was unused address. 3FC0 to 3FFF is all the WPC ASIC stuff. The ASIC is one gigantic address decode chip. It sees all the address bus bits, it decides what it wants to do, and it lights up one specific signal based on an address that it recognizes, and it's capable of breaking down all sorts of different addresses. Solenoid groups 1 to 8, solenoid group 2, 9 to 16, solenoid group 3, 17 to 28, 17 to 28, and 24, sorry, and solenoid group 4, 25 to 28. And it will discreetly break those down at the byte level and output a signal appropriately. It's much more complicated, but they fabricated a chip to do this. You try to do that on using discrete chips, you've got a lot of logic, it's expensive. So WPC further on, 4000 to 8000 is code, much like in System 11, but it's what's called bank switched. And 8000 to end of address is also code, but it's operating system. The 8000 and above is always mapped. If you touch 8000 to the end of ROM, you get the same code. If you touch anywhere in 4000 to 8000, you get whatever is switched in. So what this does is it allows different groups of 16K of code to be swapped in. You can put different functionality in different banks, and you have to switch that bank enabled in order to touch that code. And there's special code in the 8000 range that does the bank switching. Since it's always mapped, it's always the same code. If you try and bank switch 4000 to 8000, you'll swap in some code that is not yours while it's trying to execute it, and bad things will happen. So bank switching is a way for them to increase the available code space without increasing the address bits. And they couldn't increase the address bits because they were dealing with a fixed 16-bit microprocessor. In 32 bits today, they would have said, I got more than enough space than I needed, but that's not what was available in those days. So this is how address decode works at a big level. We'll focus on 15 and 14, and you'll see that what I've done is I've written them as 1514 rather than 1415. And this is because if you spent any time looking at binary, it's always MSB, most significant bit, on the left. And it works its way down through to the right, which is the LSB, the least significant bit. 2 bits, 0001, 1011. And it corresponds to 0 to 4, 4 to 8, 8 to C, and C to F. In the case of the address map for System 11, it doesn't care what address bit 14 is because it's always 8 and above, which is why there's a star there. If A15 is on, you always get U27, the primary ROM in the system. If A15 is off, it depends on what A14 is as to what you will get. If A14 is on, you get U26, ROM 2. If A14 is off, you get the low 4000, and that is further decode. This is why I call it the major decode. This is the top level of what the address decode does. So you've got A14 and A15 are 0 and 0. You need to do with more decode. Next thing to do, go look at A13. A13 is basically, we'll break it to the 4000 hex into 2000 hex sections. And you'll see that the 2000 hex corresponds to peripheral, and the 0 corresponds to RAM. And that's how they divide it up. Everything is a power of 2. Everything is half, 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 half. This granular level, this level of granularity is easy for decoding. But as I was saying earlier with the WPC ASIC, where they have byte level granularity, that requires expecting a lot of address bits and making logical decisions on a lot of address bits. More logic than you want to put on a simple board. So you can go one step further if you want, and you can go to the next 3 bits, A12, A11, and A10, and you can draw up I guess you'd call it a truth table, a matrix table of the bit patterns, 0s and 1s, and you can compute the hex address based on where it's located at 2000. And if you look at the schematic and you look at the bits and which signals go where, you'll find that those signals tie to those hex addresses and they tie to those peripherals that you see. And I didn't put the U numbers in there, but you can find them on the board. And I think if you look in the Williams schematic, you'll see that inside the peer, it's actually labeled 3400 or 2C00. And the labels there in the schematic correspond to how this address decode works. And again, you can go further as well for A0 and A9, but I'm not going to do that. So how does all this fit together? So here's your schematic. And this is my reproduction schematic because I've labeled it. It's a little bit easier to read rather than using the Williams one where I'll have to describe. But you can see here, as I was describing earlier, A15. If A15 is 1, then and all of the other inputs to this AND gate are 1. It's a NAND gate. The output that comes out is 0. That inverts all the 1s. All the 1s produce a 1 result, except the output is inverted to a 0. That signal goes up to ROM1CS, U27. And the chip select signal for the ROM is active low, which is why that output 0 activates that ROM chip. The address, the bus says A15 is 1. As soon as that happens, this decode logic goes through, produces a 0, low output on ROM1CS. The ROM chip wakes up and it says, oh, you got something for me. And it starts dealing with it. And you can see the same thing here with 14 and 15. So this 14 and 15 will deal with U26, and I'll show you how it gets U26 to be active. This is an enable bit. For this particular logical unit, it's a 2 to 4 decoder. The enable bit is tied to ground, which means this chip this logical unit is always active because it's E with a bar over it. So it's always active when it's tied to ground. So this chip is always looking at A14 and A15. And because there's 2 bits, you can either have 00, 01, 10, or 11. And guess what each of these 4 outputs correspond to? They correspond to either 0, 1, 2, or 3. And because the way that I did this schematic symbol with that 45-degree angle line, that means the signal is active low. So when the signal comes out and it's active, it's low. You can see here there's Y0, Y1, Y2, and Y3. You can pretty much guess what they correspond to. Y3 corresponds to 1, 1, Y2 corresponds to 1, 0, Y1 corresponds to 0, 1, and Y0 corresponds to 0, 0. So what this chip is doing is it's looking for specifically a 0, 0 configuration because it's ignoring everything else. It says 0, 1, I don't care, 1, 0, I don't care, 1, 1, it's only looking for 0, 0, which corresponds to that further decode between 0 and 4000. So what happens here? This signal comes out as 0. So as soon as it comes out as 0, the rest of this cascades to 0 because this is an AND gate. If one signal is 0, the output is always 0. So this output becomes 0. Well, that gets fed into this NAND gate, which means that both outputs have to be 1 in order to be true. If either input is 0, both inputs have to be 1. If either input is 0, that automatically makes the output 0. And with the output 0, it's NAND, it inverts it, it becomes 1. What does that do? That signal goes up to ROM2CS. Well, what that means is that as soon as this is 0, 0, ROM2CS is disabled because you've outputted a 1. The way to get ROM2CS to enable is to output a low. So what conditions output a low? In order for this to be outputting low, 0, it has to be fed 1. So both of these signals have to be 1. This signal, the top signal, is 1 when both of these signals are 1. When both of these signals are 1 when it's not 0, 0. In other words, for A14 and A15, in other words, it's looking specifically for 4000, 8000, or C0. What about this other signal here? This other signal here is VMA and E. I'm not going to go into that as so much as to say is when everything's valid, that's 1. So what happens here is if you touch, for example, if you touch 4000, you want to get to U26. These two signals are 0, 1. That produces a 1 on Y0 because it's only interested in seeing 0, 0. Because that produces a 1, this input is 1. This input is 1 because it comes from E and VMAs. That produces a 1 to this. But wait, what about this other signal? If you look at this other signal, if A15 is 0 because we're touching 4000, not 8000, that produces a 0, which produces a 1 output here, because again, any one of those is 0, the output becomes 1. This is 1, that feeds a 1 into here, that feeds a 1 into here, both of them are 1, this output becomes 0, guess what happens? ROM2CS goes 0. It's automatically selected, you've touched 4000, this chip says it's for me. That's how this address decode works, but you have to walk through it. You have to look at the logic. What happens at 0? What happens if 1 here? And if you work through it, you'll see that this actually produces the right result. ROM1CS is enabled when it's 8000 and above. ROM2CS is enabled only for 4000 to 8000. Now, let's go cover between the 2000 address, the peripheral, because we've covered the 4 and we've covered the 8+. So how does the peripheral select work? Well, this fancy chip here, the 74LS138, is a 3 to 8 decoder. If you feed 3 bits in, you get 1 of 8 results out. That's what 2 to the power of 3 is. It's 8. What is it specifically looking at? It's looking at VMA, valid memory address, active high. Again, you assume that's high. Then it's looking at A14 and A15. And both of these are active low, which means that you have to be selecting less than 4000. So if you've got VMA and less than 4000, then this chip wakes up and it says, oh, you have something that's less than 4000. You must have something for me. And it starts decoding these address bits. And what does it do? Well, I think if you look there, 10, 11, and 12, that's this table. And if you look here, you'll see that I put the bit patterns there, 0000, blah, 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 and the corresponding hex and what it is. But you really only need to see the hex address here. Because if you look at the next, you'll see that it goes from Y0 to Y7. And what's it looking at? It's looking at 2000, 24, 28, 2C, 30, 34, 38, and 3C. And all that does is it sends the corresponding signal to the chip select pin of that peer. And all the other chip select pins are whatever they need to be, static or not static based on a high address. That is how the chip select works. It just takes those address bits, figures out what it is from 3 to 4, activates only when it's in the 00 range with a valid memory address. Boom, out it goes. Well, what happens with 2400? That goes up there. That's further up. I'm not going to get into it. If you also look here, you see, I think in oops, in this slide here, I had A8 and A9. And you can see that there's further address decode here from 2000. Why 0? 2000? It feeds into enable. So this chip is enabled when 2000 is active, and it further decodes address bits 8 and 9 into whatever those are. And you'll see here 00, which is 2000, is not used. 2100 goes to the peer that's located at 2100. 2200 is another signal. It goes up. I'll tell you now, that's a latch. It's a specific, you want to get a solenoid, you touch 2200, you write the bit pattern that you want, and those solenoids from 1 to 8 get activated. And 2300 is not used. That's address decode. You got to sit down, you got to work through it, you got to get all your bit patterns. But once you look at this, you'll figure, oh, that's how it's supposed to work. And I think that's it. I hope that wasn't too much. If anybody has any questions. The microphone?
Try now. There we go.
Yep.
You touched on reset. What's reset?
Reset is, so when you apply power to a system, there is a special IC called a voltage supervisor on more modern machines. On the original System 11, it's an RC circuit, and I don't want to go into the details of the RC circuit. I think it's easier to think of it as a like a modern IC, a reset supervisor, a voltage supervisor. The voltage supervisor watches the voltage coming in, the 5 volt, and when it rises above a certain level, it will release the processor from reset. So what does this mean? The output of the voltage supervisor is 0, low, and it is held low until the voltage stabilizes above 4.75 typically. And then once the voltage is above 4.75, that reset signal to the processor will go high. When it goes high, the processor is released from reset and it starts executing. The reason why these systems exist is because if the voltage goes low, it produces voltage levels in TTL that are in what I call no man's land. They're neither definitive for high or low. And because they're not definitive for high or low, the hardware is not guaranteed to produce the correct output of a high signal or a low signal. When the hardware is not guaranteed to do that, the software is not guaranteed to execute properly. And if you get incoherent random software execution because hardware is failing, you as a software developer will get frustrated pretty quickly. So what the hardware people do is they say, oh, you've entered indeterminate voltage territory, reset. And by doing that, it resets the system back. And often the indeterminate voltage territory is entered because of too much of a load on the system. You've drawn too much current somewhere. So the easiest way to restore the load is to stop the software from executing, which withdraws all the load, and boom, everything comes back up. So what do processors typically do when they're released from reset? They have a specific pattern of execution and a known state. All the registers are zeroed. The program counter, the PC, is set to a specific value, or a value is fetched from a specific known location. And that program counter is loaded and program execution starts. Every processor has a reset vector, an address that is either where it will jump to directly when it comes out of reset, or an address of memory location that it will jump to where it comes out of reset. In the 6800, that reset vector is located at the highest 2 bytes of memory, FFFE and FFFF. The processor comes out of reset, loads those 2 bytes, puts them into the program counter, and starts executing from that address. That's what reset is. Did that answer your question? Okay.
Hi, Victor. You mentioned as far as the data register and as far as the values being A, B, X, and Y. And this is kind of outside the realm of pinball, but as far as those 4 values, came to mind as far as a Nintendo Switch.
So no, those are names of registers.
Okay.
So if you look at instructions, you'll see LDAA, load accumulator A, or LDAB, load accumulator B. Those are just simple names for those registers. They call them A and B because that's how creative they are.
Okay. So it has nothing, as far as, again, just a coincidence that the Nintendo Switch
Yep.
has those four.
Yep. No relevance at all.
Okay.
It's just the people who designed the mnemonics and the processor, they just called it accumulator A and accumulator B.
Okay. Thank you.
Yeah. If you're familiar with the Intel world, you'll also see they have accumulator registers A, AX, I think it is, and BX, and CX and DX, and you'll see those. It's just they use A, B, C, and D. That's just what they do.
Yeah, follow up on the reset. When it goes into reset condition, does it also typically work in a system that it clears registers and flags, or does it leave those alone?
So when a processor comes out of reset, it is always in a known state. It is a specified state. You know what it is.
Hi, Victor. So you touched on this briefly, but let's say you have like a binary dump from an EEPROM, and sometimes you have to do like a byte swap to change from little to big endian, or vice versa. That seems to be almost like the way the data is represented. Most significant, less significant byte seems to be from the reading software. So if it's actually, I'm just wondering, in terms of the endian representation, is that specific to the IC manufacturer, or is that the way the CPU would read it out and interpret the data?
It's processor specific. So in the Intel world, everything is little endian. That is how Intel operates. They are always little endian. If you look at the for the 8-bit microcontrollers, the 6502 is a little endian processor. It's not Intel, right? The Motorola world, the 6800, 6802, Motorola is always big endian. So if you've got code that's written for Motorola, you'll always have data that's in big endian format. And it doesn't matter because you won't be able to execute that code on a little endian machine because the instructions are different. It's completely different instruction to the architecture.
Right.
They're not compatible.
Okay.
However, if you want to take that data, for argument's sake, it's a 16-bit data, and you want to use it in some other system, pixel data, for example, or some other sound data if it's 16-bit data, you're going to have to know what system it came from, what the endianness native to that system is, and swap the bytes accordingly if you need to.
I guess another case would be, I guess, if, let's say, you wrote some type of emulation software that's interpreting, trying to interpret the binary, then you'd have to know what the endian representation is.
You just have to make that assumption. So a long time ago, I worked on a project that required endian conversion, and the software was originally written for a little endian machine, and we were running it on a big endian processor. And every single instruction that we had to interpret, we had to swap the data. It was 32 bits, so we did 32-bit endian swaps. That's just how it worked. The biggest grief was floating point data.
So I guess if you're saying it between Motorola or Intel, the hardware is storing it differently. I guess if it's being read out, the CPU can also do some interpretation.
So some
data manipulation, right?
Some processors will have endian swapping support. Right. So if you're familiar with PowerPC, there are specific instructions that will do byte reversals. So in PowerPC, there's load, word, and zero. Standard big endian load, IBM processor, PowerPC. There was also an instruction, load, word, byte reversal index, that will load the same 32 bits but perform a 32-bit byte swap as it's loaded, so that the result in the data register is the correct 32 bits read appropriately.
Right.
It's up to the processor, it's up to the system you're working on.
Right, okay, thank you.